chemical reactions proceed at different rates. The factors that affect these rates are the surface area of a solid reactant, the concentration or pressure of that reactant, the temperature, the nature of those reactants, and the presence or absence of a catalyst.
But this time, we will only focus on three: concentration, temperature, and catalyst. Concentration. The concentration of a substance can be expressed in a variety of ways depending on the nature of a substance. Aqueous solutions typically have their concentrations expressed in mole over L. For example, a solution made by dissolving sodium hydroxide in water has its concentration expressed as moles of NaOH per liter of solution. Gases can also have their concentrations expressed in mole over L. In terms of the collision theory, increasing the concentration of a reactant increases in the number of collisions between the reacting species per second and therefore increases the reaction rate. You can change the concentration of an aqueous species by simply adding more solute to make it more concentrated or adding more solvent to make it more dilute. You can change the concentration of a gas by adding more gas to a fixed volume or by decreasing the volume of the container. Conversely, the concentration of a gas can be decreased by removing a gas from a fixed volume or by increasing the volume of the container. Temperature. With the exception of some precipitation reactions involving ionic compounds in solution, just about all chemical reactions take place at a faster rate at higher temperatures. The question is, why? Temperature in Kelvin degrees is proportional to the kinetic energy of the particles in a substance. For example, if the Kelvin temperature of a substance is doubled, then the average kinetic energy of the particles in that substance is doubled. At higher temperatures, particles collide more frequently and with greater intensity. Here's an analogy. Imagine that you are babysitting a bunch of 6 years old. You put them in a yard and you let them run around. Every now and then, a couple of kids will run into each other. Now imagine that you decide to feed them some sugar. What happens? They run around faster and of course, there are many more collisions. Not only that, the collisions are likely to be a lot harder or more intense. Catalyst. A catalyst is a species that speeds up a chemical reaction without being chemically changed upon completion of reaction. In other words, the mass of a catalyst is the same before and after a reaction occurs. Common examples of catalysts include MnO2 in the decomposition of H2O2, Fe in the manufacture of NH3, and Pt in the conversion of NO and CO to N2 and CO2. Recall that collisions only result in reactions if the particles collide with enough energy to get the reaction started. Also, recall that activation energy corresponds to threshold energy. As you can see in this graph, only collisions involving particles with sufficient kinetic energy results in the formation of an activated complex. Particles processing less than the threshold energy simply bounce apart upon collision. The number of successful collisions per unit of time be increased by lowering the threshold energy, or in terms of potential energy, lowering the activation energy. Adding the appropriate catalyst to a chemical system has exactly this effect on the threshold or activation energy. A catalyst provides an alternative pathway for the reaction, a pathway that has a lower activation energy. The catalyzed pathway has lower activation energy. Relating this back to the kinetic energy diagram, you see that more particles will have sufficient kinetic energy to react. In other words, the addition of the catalyst increases the reaction rate.